Now, we define the least element of a non-empty subset of natural number. Let S be a subset of natural numbers, and it is non-empty. An element M of S is called the least element if M is less than or equal to S for all S in S. An interesting property of N is that every non-empty subset has a least element. This property is called the well-ordering principle of N. Equivalence of well-ordering principle, or WOP, of the set of natural numbers and the principle of mathematical induction, or PMI. WOP says every non-empty subset of natural numbers has the least element. If S is a non-empty set, then there exists an element M which is less than or equal to any other element X. Whereas PMI says that if a proposition holds true at n equals 0, and the truthness of the proposition at n equals k implies the truthness at n equals k plus 1, then the proposition holds true for all natural numbers n. We shall establish the logical equivalence of these two principles. This means the fifth axiom of Peano is equivalent to the well-ordering principle of natural numbers. Now, assuming that WOP is true, we are going to prove PMI. S is a set in which all the conditions of PMI hold, that is, 0 is in S, and whenever n equals k is in S, then n equals k plus 1 is in S. We shall show that by using WOP, S equals n. Suppose S is not equal to n, then the complement of S in n is a non-empty set T. So, by the well-ordering principle, T has a least element M. It is the crucial step where the WOP comes into the picture to arrive to the contradiction. Next, let us analyze the possible values of M or properties of M. M cannot be 0, because 0 is in the complement S of T. It means M minus 1 is a natural number, but M minus 1 cannot be in T, because M is the smallest element of T. It follows that M minus 1 is in S. So, by PM, I condition K equals M minus 1 is in S means K plus 1 equals M is in S also. M was a natural number such that it is the least element of T, the complement of S. So, M is in T means M cannot be in S. So in one way, M is in S, and at the same time, M is not in S. This is a contradiction. This contradiction arises from our assumption that S is not equal to N. Therefore, if the conditions of PMY hold on S, then the conclusion of the PMI must also hold on S. Hence, S equals N. Next, we prove that principle of mathematical induction implies the well-ordering principle of the set of natural numbers. Let T be any non-empty subset of natural numbers. Using the principle of mathematical induction, we are going to show that T has the least element. Assume that T has no least element. That means for all M in T, there is an element A in T such that A is less than M. Let S be the complement of T in N. That means an element X is in S if and only if it is not in T, and vice versa. Next, we prove that 0 is in S. If 0 is in T, then 0 would be the least element. But T has no least element, which implies that 0 is not in T. Therefore, 0 is in S. Next is the strong induction hypothesis. That is, assume that all the elements from 0 to k are in S. We shall show that k plus 1 is also in S. If possible, suppose k plus 1 is in T. All elements from 0 to k are not in T. This implies every element of T is greater than or equal to k plus 1. The next step is the contradiction step. The above analysis shows that k plus 1 is the least element of T. But, by our assumption, T has no least element. Therefore, k plus 1 must be in S. So, S is a subset of N such that all the conditions of the principle of mathematical induction hold, so S equals N. This means T is empty set. But T is a non-empty set. Therefore, our assumption was false. So, T must have the least element. Hence, PMI implies WOP.